In this video, we're going to be looking at radicals simplification. We're going to simplify radicals, and most of the time when you guys see this symbol right here, you're assuming you call it a square root, which in this case, what you see on your screen, it does represent the square root. But a radical is anything that has a root. We could have a cube root, a fourth root, a fifth root, but we are going to deal with square roots in particular with this one, because we're going to be dealing with the Pythagorean theorem and the distance formula, which does entail using square roots. So let's look at some basics here and kind of understand the foundation. First of all, what is a square root? Well, a square root is a number that we actually multiplied by itself to get another number. That's what it's asking when we do square root. So if I ask you, what is the square root of 25? You're going to tell me that's 5. And the reason it's 5 is because 5 squared equals 25. So the square root would be 5. Where does this terminology come from? Well, first of all, the square root is based on the actual shape of a square. So if I give you a square, and I'm going to indicate it's a square by giving you 4 right angles and 4 congruent sides. What squaring and square rooting have to do with is the actual area and the side lengths of a square. So let's say I gave you a 5 by 5 square. Now we know that that implies that the rest of the sides, the other 2 sides, are also 5 because this is a square. But just for our purposes, I'm only going to write those 2. What would be the area of my square? Well, remember, the area of a square is length times width, which you will see sometimes written as side squared for a square because all the sides are the same. Sometimes you'll see it written like this. But let's get very simple. A square is a type of rectangle, and we know a square is length times width. Length times width for this square would be 5 times 5, which is 25. So the area of my square is 25. Now hopefully you can see that there is a connection between the side lengths and the area. So let's look at the terminology. First of all, square root. So this is the square root. What a square root is actually asking is, if you have a square that has this as an area, how long are the sides? So if a square has an area of 25, what are the lengths of the sides? That's what a square root means. On the other hand, over here you have squared. And what squared is asking for is, if the lengths of the side of your square are 5, what is the area of your square? So to take the square root, we have the area, and we get the side. And to square it, we have the side, and we want the area. Now, if I were to write that out with words, this is actually what it would look like. And it's important that you understand the representations here, because it makes the actual operation make more sense. So when we take the square root of something, we want to know from the area what the side length was. By the same token, if we come over here, when we take the side and we actually square it, what we're looking for is the actual area of the square. So you can see how that works with the terminology and what it means to be squared and square root. So when we simplify square roots, we have a whole host of square roots that you guys have seen before. For example, the square root of 4 is 2. Why? Because 2 squared is 4. The square root of 9 is 3. Why? Because 3 squared is 9. The square root of 16 is 4. Why is that? Because 16 is 4 squared, and so on and so on. You're familiar with a bunch of square roots, but that's what they mean. And so technically, the square root of 4 is telling me what's the square root of 2 times 2. The square root of 9 is asking me what's the square root of 3 times 3. And the square root of 16 is asking me what's the square root of 4 times 4. And what you see here is every pair can be square rooted to get a single. I have a pair of 2's. Well, what's the square root of 2 times 2? It's 4, which is the square root of 4, which is 2. What's the square root of 3 times 3? Well, the square root of 9, which is just 3. And what's the square root of 16? Well, that's the square root of 4 times 4, which is 4. So, do you see a pattern here? For every pair, I can bring one outside the radical sign. So now we're going to look at actually simplifying these radicals. And I'm going to show you a couple of methods on how to do it. So when we simplify, a lot of times we want, if you see something like this, for example, let's do, okay, so we're going to call this simplifying radicals. So for simplifying radicals, a lot of times you'll see something like this. Square root of 8. And for square root of 8, you'll punch that into your calculator and you'll get 2.8 or 2.9, something like that. Well, when we simplify radicals, we don't want decimal values. We actually want to keep it in radical form with the radical, or the square root in this case, symbol or structure. So there's several things we can do. The first one is doing the factor tree. So we're going to do our factor tree. So I'm going to take 8 and I'm going to factor it out using a factor tree. So 8 can be broken down into 2 times 4. 2 is a prime number. And remember, when we talk about prime numbers, and I'll make a little note over here. Prime numbers are numbers that only have the number itself and 1 as factors. So 2 is prime. The only factors of 2 are 2 and 1. 2 is prime. We're done. 4 is not prime. We can keep going. 4 can actually be factored. So 4 can be factored into 2 times 2. And I'm going to circle my roots. That's as far as I can go with that factor tree. So what I'm going to do is I'm going to come over here and I'm going to rewrite the square root of 8 as a set of factors. And in this case, I have 2 times 2 times 2. Once you actually break this down into its prime factors, the next thing you look for are pairs. If you go back to the previous document where we were working, you notice over here on the side what happens when you have a pair. Trying to get my cursor to show up here. I don't know where it went. It's kind of stuck. But you can see that you've got pairs of numbers here. And for every pair, one comes outside, because technically a pair is something squared, right? And the square root of something squared is that something. One thing that you need to realize is that just like addition and subtraction are inverse operations, multiplication and division are inverse operations, square root and squaring are inverse operations. For example, 5 and negative 5 are inverses. They'll cancel each other out. Okay? If I multiply by 5 and then I divide by 5, those cancel each other out. Okay? That gets me to 1 in a lot of cases. You have 5 and 1 over 5. So those are inverses of each other. That's called a multiplicative inverse, and that's an additive inverse. Squaring something, if I do 5 squared, if I square root it, I undo it. That's just 5. The radical and the squared cancel. Just like here, the plus and the minus cancel. The plus and the minus cancel. The multiplication and the division reduce. So those are inverse operations. So if I come back over here, I have a pair. I'm going to look for all the pairs. I've got a pair there. And remember, every pair, 1 comes out, because that's technically 2 squared, right? Or the square root of 4, which is just 2. And then I have this guy here that has no partner, so he just stays underneath. So there is the square root of 8 simplified. Let's look at another one. Let's look at the square root of 10. Well, if I look at the square root of 10, I'm going to take 10 and I'm going to factor it out, and I get 2 times 5. Now, 2 and 5 are both prime numbers, so I can't factor this anymore. So I technically have the square root of 2 times 5. Do you see any pairs there? There are none, which means I just multiply them back. That means that square root of 10 is already simplified. That's as simplified as you can get it. There are no pairs. There's no way for you to simplify this. Okay? So let's pick another number. Let's do the square root of 18. Well, I'm going to take 18 and I'm going to do my factor tree. Again, my program's being a little wonky. So I have 2 times 9. 2 is prime. Can't go any further with that. But I can factor the 9. So I'm going to go ahead and factor 9. 9 is, and again, I don't know why my program's messing up, is 3 times 3. And guess what? 3 and 3 are both prime. So I'm done factoring out 18. So 18 is basically 2 times 3 times 3. And what we're looking for are buddies or partners or pairs, right? I do have, if you look up here, I was looking for pairs. I didn't have any pairs on 10. I did on 8. I'm looking for pairs. I have a pair of 3s. For every pair, 1 comes out. And then I've got that 2 underneath, which doesn't have a buddy. So 3 square root of 2 is the simplified form of square root of 18. So you can see when you have a pair, it comes out, 1 comes out, and anything left is remultiplied back together. Sometimes, like in the case of square root of 10, we don't have pairs. Get this, see if I can erase that. Nope. We don't have any pairs, so it's already simple and simplified. So let's look at something that might be a little more complex. Let's look at the square root of, let's see here. I'm going to try to think of something that, let's look at the square root of 72. So I'm going to take 72 and I'm going to factor it. Now, there are multiple ways you can go on this. You can do 2 times 36. You can do 9 times 8. There's multiple ways. You can do 4 times 18. However you want to start it off, you'll end up in the same spot. So I'm going to do 8 times 9. And neither of those is prime. So I've got to keep going. So I'm going to take the 8 and I'm going to make that 2 times 4. 2 is prime, so I'm going to stop there. But the 4 is not prime, so I'm going to keep going. And that's 2 times 2. Both of those are prime, so I'm done on that side of the tree. Let's go to 9. 9 is 3 times 3. That's your only option. And 3 and 3 are both prime. Again, prime numbers are numbers whose only factor are themselves and 1. So I'm going to write 72, rewrite it as 2 times 2 times 2. I've got 3 2's here. Times 3 times 3. So now I'm looking for my pairs. Well, what do you notice here? Not only do I have 1 pair, I've got 2 pairs. So what do I do with that? Well, I'm going to take the 2 out, because remember, that's 2 squared, and the square root of 2 squared is 2. I'm going to take the 3 out, and again, this is all multiplication, so everything that you pull out and leave under is all multiplied together. And what's left without a buddy underneath? The 2. So 2 times 3, I'm going to multiply those together, is 6. And I've got square root of 2 left underneath. So that's how you do with multiple pairs. Each pair is 1 comes out, and you multiply it. So we've looked at simples, where you have 1 pair only, like 8 and 18. Terms where you don't have any pairs, like 10, and it's already simplified. And now terms where we have multiple pairs. So if there are no pairs, it's already as simple as it can get. If there are multiple pairs, you take 1 out for each. If there's only 1 pair, you take 1 out. But let's go even further, and let's look at one more example. And let's look at, let's see here. let's look at the square root of, I'm trying to think of something good to give you, the square root of 100. Okay, so let's factor 100. I'm going to factor 100 as 4 times 25. Neither of those guys is prime, so I'm going to factor them out as 2 times 2. That's done. I can't factor anymore, and I'm going to factor 25 as 5 times 5. So now I'm ready to write 100 as the square root of 2 times 2 times 5 times 5. My next step, let's look for pairs. We've got 2 pairs. I've got a pair of 2's, so the 2 comes out, and again, this is all multiplication. I've got a pair of 5's, so the 5 comes out, but there's nothing left underneath. What does that mean? Well, if everything pairs up, what that means is your number is a perfect square. 100 is a perfect square. So square root of 100 is actually just 10. So when you don't have anything left under the radical, it's a perfect square. So these are all the different, this is the one method you can use to simplify all these, okay? But if you want to do it a different way, you can. Now I'm going to erase this. Remember, we know now that all prime numbers have a factor of 1 in themselves. Well, let's look at a different method. Let's take square root of 8 and let's break it down. So the square root of 8, remember when you do radicals, it's all multiplication. So I broke this down into 2 times 4. We're not using the factor tree now. But let's look carefully at this. I can actually break these apart. That's one of the rules of radicals. Square root of 8 is actually the same thing as the square root of 2 times the square root of 4. Well, guys, what is the square root of 4? It's actually 2, right? 4 is a perfect square. And then what's left underneath? Square root of 2. Do you see how these are the exact same? And I went 2 different methods. I looked for perfect squares. Sometimes you'll want to look and see if there's a perfect square. Now, obviously, we couldn't factor 10. Is 10 going to have a perfect square? No. 10 won't have a perfect square. If you wrote square root of 10 and you tried to break it apart into the square root of 2 times 5, that would be the square root of 2 times the square root of 5. You don't have any perfect squares there, right? We're right back where we started, square root of 10. Let's look at 18. Let's take square root of 18. That's the same thing as the square root of 2 times 9, which is the same thing as the square root of 2 times the square root of 9. And now I've got a perfect square. What's the square root of 9? 3. And what's left over? Square root of 2. Once again, same answer. Same answer. Let's look at 72. If I do square root of 72, and I'll write it up here because of space, I can make that the square root of 9 times 8. But you know what? I could also make this the square root of 9 times 2 times 4, which is actually the square root of 9 times the square root of 2 times the square root of 4. And what are my factors? Well, what's the square root of 4? It's 2. What's the square root of 9? It's 3. What's left underneath? Square root of 2. And what's 2 times 3? 6. Square root of 2. Same answer, guys. And the thing about 72 that you could have also done, I could have written 72 as the square root of 36 times the square root of 2, right? Same thing. And I would have had square root of 36 times square root of 2. Well, what's the square root of 36? 6. And what's left underneath? Square root of 2. So you can see that there's multiple ways you can do this and solve it. It's just whatever's easiest for you.